The next topic in chapter number 6 is the concept of total area. And for total area, I'm going to graph the equation, and then after that, we're going to find the area underneath the curve. And regardless if the area is underneath the x-axis or not, we always assume that the area is going to be positive when we're dealing with total area. So before we get to some more total area questions, let's do a few practice questions, starting with example number 1. For example number 1, I have a quadratic right here. So let's go ahead and do a simple sketch of the quadratic first. So I don't need a very detailed graph of the quadratic, I just need a very basic sketch. So this is y equals to x squared plus 1. And I want to find the total area between 0 and 2. So here is 0 and here is 2. And the area that we're looking for is this green area right there. So for this particular question, we don't really need to modify anything. It's a straightforward finding the area underneath the curve. So if I want to set my integral for this problem, the integral would be from 0 to 2, and my equation is x squared plus 1, and then we're going to times this by dx. And after that, we can just take the antiderivative of the middle term here, and the antiderivative of that is going to be x to the power 3 divided by 3 plus x. And then after that, we can put this into a bracket here, square brackets, and I can put my lower bound here and my upper bound there. And based on the fundamental theorem of calculus, we always evaluate the upper bound first. So the upper bound would go into the x values. So that's going to be 2 to the power of 3 divided by 3 plus 2. And I'll put that in a bracket there. And then I need to subtract the lower bound now. So I will put 0 now in for x and x. And this one's simply going to be 0 cubed over 3 plus 0. And that whole bracket there just goes to 0 anyways. So after that, we just need to evaluate this yellow expression right here. Okay, so 2 to the power 3 is going to be 8. So 8 over 3 plus 2. Now 8 over 3 plus 2 is going to be 14 over 3, and that's going to be my final answer there. Okay, so just going back to my sketch again, what we've discovered here is the area over here. That green area represents 14 over 3. So that's the area underneath the graph for this particular question. Okay, let's go on to a trig question now. I got y equals to cos x, and I want to go from pi over 2 to pi. So I want to find the total area here. So for the total area, let's go ahead and do a simple sketch here. And cos x starts at a maximum. So it goes from a maximum down low, and then we go back up to a max again. And pi is going to be over here, and this is going to be pi over 2. And basically, I want to find the area underneath the graph from pi over 2 to pi. So I want to find that green area. Now, because the area is underneath the x-axis, technically it is negative, but for total area, we always assume that the area is going to be positive regardless if the area is below the x-axis. Now, in order to illustrate that, let's go ahead and set up the integral first. So the integral is going to go from pi over 2 all the way to pi. And my function is going to be cos x, so I need a cos x right here, and then I'll multiply that by dx. Now, if you go ahead and actually calculate this, you will get a negative answer. So in order for us to modify the answer so the answer is always positive, you can just put an absolute value sign around this whole expression here, and that will ensure you that the final answer is indeed positive. Now, there's different ways where you can take a area underneath the graph and make it positive, but I think just having the absolute value signs there, that's just a very simple way to kind of make the negative answer into a positive answer. Okay, let's go ahead and find the antiderivative now of cos x, and using my formula right here, the antiderivative of cos x is going to be sine x. So let's go ahead and put this in a bracket here. So the antiderivative of cos x is going to be sine x, and I'm going from pi over 2 all the way to pi. So this is the problem that I need to evaluate now. And based on the fundamental theorem of calculus, let's go ahead and plug in pi first. So this will be sine of pi. And then the fundamental theorem of calculus states that we need to subtract the lower boundary now, and now we need to find sine of pi over 2. All right, so this is the expression here. Now we need to go out there and actually evaluate this. And if you've forgotten how to find sine pi and sine of pi over 2, it might be in your best interest to do a simple sketch of the graph on the side here. So I'll do a simple sketch of the graph in green here, and sine x goes like this. And this is going to be pi right here, and this is going to be pi over 2. So pi over 2 has a height of 1, and sine of pi has a height of 0. So sine of pi is going to be 0, and sine of pi over 2 is going to be 1. Now remember, we're putting the absolute value around this whole thing. So I know that I know 0 minus 1 is going to be negative 1, and the absolute value of negative 1 is going to be positive 1. So positive 1, this is your total area. Because the concept of total area is we always assume that the area is going to be positive regardless if it's underneath the x-axis or not. Now, if I go back to my graph here, I did mention that if we're just finding the area underneath this graph, yes, this area would be negative 1 if we're just finding a regular area. But since we're asking to find total area, we just assume that the answer is going to be positive. Okay, let's move on to a few more questions where we need to do some more calculations here. And whenever you're doing total area questions, always do a sketch. Never jump to the integral. You want to have a good feel of what the graph looks like, and then once you have that, you can set up your integral. And then the real challenge is working through the calculations so that you don't make any simple mistakes. Now for the next one, I have another quadratic here. Let's go ahead and factor out a 3x. So if I factor out a 3x, I would get x minus 2. So 3x times x minus 2. And I know my zeros are going to be at 0 and at 2. And this is going to open up because we have a positive leading coefficient. Okay, so let's go ahead and do a simple sketch of this graph here. So here is 0 and here is 2. And let's go ahead and graph this going up like that. 0 and 2. So that's 2 and that's going to be 0. And what we need to do is we need to find the total area from 0 to 3. Okay, so for this particular problem, let me just kind of modify this a little bit here. Let's just say 3 is over here. And I might have to just change my graph slightly here so that just fits this. Okay, that's a better graph of my, that's a better sketch here. Okay, so I want to find the area underneath the graph between 0 and 3. So from 0 to 2, this is my area from 0 to 2. And then from 0 to 3, from 2 to 3, I need to get this area right here. Okay, so in order to find the total area for this particular problem, I need to find the area in the green region and the area in the yellow region, add them together, and that would be my total area. And we always assume that the total area is going to be positive. Okay, so let's take a look at this green region right here. We know that area is going to be negative because it's underneath the x-axis, but let's go ahead and set up the integral for that. So the integral is going to be from 0 to 2. And my equation is going to be 3x squared minus 6x, and then I'm going to put the dx right here. Now that area will be negative because it's underneath the x-axis, so in order to change the positive, let's just go ahead and put the absolute value signs around that integral. And then let's go ahead and take a look at this yellow region here, because total areas, I need to find the combined areas here. This integral is now going from 2 to 3, and my equation is still going to be the same. It's going to be 3x squared minus 6x, and then we're going to multiply that by dx. And this whole thing is now called the total area, right? So total area is, we always assume that the areas are positive, and then we just add up all the individual areas together. Okay, so that's my setup here, and once again, if you have a graph, then setting up your integral is not too hard. And I think the real challenge now with these kind of problems is making sure you can do the antiderivative, the fundamental theorem of calculus, and finding the right numbers. So our attention to detail has to be pretty good. Okay, let's go ahead and evaluate the first integral, the absolute value sign. Okay, if I want to find the antiderivative of this quadratic right there, that one's not too bad. The 3 remains the same, but the x squared, we need to add a 1 here. So that's going to be x to the power 3 divided by 3 minus 6 times x squared divided by 2. And then I can put that into a bracket here. And I'm going from 0 to 2 there. And remember, we're taking the absolute value of this entire expression there. So I will work with this integral first, and then I'll move on to the second integral after I'm done. Okay, let's go ahead and just simplify this. Those will cancel off, and that will give you x cubed minus, and then 6 divided by 2 is going to be 3. So this will be a 3x squared, going from 0 to 2. And let's put the absolute values at the very end. And then the fundamental theorem in calculus states that we need to do the upper bound first. So let's go ahead and plug in the upper bound there. So this is going to be 2 to the power 3 minus 3 times 2 squared. So square bracket, and then we're going to absolute value all of that. And let's go ahead and now calculate this. This will be 8 minus, now 2 to the power 2 is going to be 4. And 4 times 3 is going to be 12. So 8 minus 12. And let's just go ahead and do the brackets here again. And 8 minus 12 is going to be negative 4. And if I put the absolute value around the negative 4, we end up getting a final answer of just 4 there. Okay, so the first area is going to be 4. And let's just go back to the top here. Let me just erase all this now. So if I'm finding the total area, this is going to be just 4 here, plus. And now let's go on to the second integral right here. So after that, I want to evaluate this now. And what I can do is I can just let's go ahead and copy this part right here. That part, I can copy that part down because it is the same antiderivative. So I want this to be x cubed minus 3x squared. So I'm just going to copy this part over there. But now my boundaries are now going from 2 to 3. Okay. And then after that, I'll just erase all this. I don't need this anymore. Okay, I'm going from 2 to 3 now. And the fundamental theorem calculus states that I need to do the upper bound first. So let's do that. That's going to be 3 to the power 3 minus 3 times 3 squared. And I'll put that in a bracket. Minus, and then we do the lower bound now. So the lower bound is going to be 2 to the power 3 minus 3 times 2 all squared, and then I'll close that. Okay, so that's the setup for the second integral, and then after that, let's go ahead and just calculate this. 3 to the power 3 is going to be 27. So 27 minus, and then 3 to the power 2 here is going to be 9, and 9 times 3 is going to be 27 as well. Minus, and then over here I have 2 to the power 3, which is going to be 8, minus, and then I have 2 to the power 2, which is 4, and 4 times 3 is going to be 12. Okay, after that we can see that this part will give you 0, minus, and this part here is going to be negative 4. And remember, when you have a negative and a negative, that gives you positive 4. Okay, so what we're really doing in terms of finding the total area now, remember the first integral was 4, and my second integral is also 4. So 4 plus 4 is going to be 8. So my final answer here is going to be 8, because I'm simply adding the two 4's together. So my total area is going to be 8, and let's just go back to my diagram here. So so this yellow area had an area of 4, and this green area had a well, it was technically negative 4, but the absolute value of negative 4 is going to be 4. So 4 plus 4 is going to be 8. So that's my total area for that particular problem. Okay, let's keep on going along. I think the concepts are, I hope the concept of total area is clear now. It just means that you're finding the combined areas there, and you might have to spend a little bit of time just calculating and going through the algebra at times.